Hello everyone, this is Professor Roman. Welcome to the sixth video in my video lecture series, An Introduction to Discrete Mathematics. We've been talking about cardinalities of infinite sets, one-to-one correspondence between infinite sets. Let's continue that discussion. Here is a theorem. Let sigma be a finite alphabet. Then the set sigma star of all words over sigma is countably infinite. And as to the proof, this will give us a chance to use the idea of a sequence, an infinite sequence, that I talked about in the last lecture. So suppose the alphabet just consists of the letters S1 through Sn. We can construct a one-to-one correspondence from the natural numbers to sigma star in the following way. First, it's important to note that for a given size m, the number of words of length m is finite. The alphabet is finite. The length is fixed at m. There are, in fact, n to the power m words of length m. We're going to prove things like this when we get to the section later in the course on counting techniques, but I think you could probably sort it out yourself if you want to give it some thought. Either that or you can just accept it now. So, to create a complete list of the words in sigma star, we can first list the one and only word in sigma naught, which is the empty word, only word with length 0. Follow this by the words of length in sigma sub 1, words of length 1. There are n of those, because n is the size of the alphabet. Follow those by the n squared words of length sigma 2, and so on. So this will result in an infinite list, or I should say a complete list of the words in sigma star. And it does require a little bit of discussion. Why is this list not finite? And you could argue something like, well, if it was finite, it would have a certain size n. Well, I shouldn't use n. That's taken. Certain size m, and argue that eventually you will have more words in your list than m words, and so the list cannot be finite. I'll let you sort out the details if you're interested. But the point is, we have a non-finite list or sequence consisting of all the words in sigma star, each word appearing exactly once, and so sigma star is countably infinite. Let me just mention, I'm having some allergy problems, so you may notice my voice is a little hoarse, and hopefully this will pass with the weather changing. Anyway, infinite cardinality is what I would call sticky, and that's not a technical term, so let me explain what I mean. If we toss some additional elements into a finite set, it will increase the size or cardinality of the set. That's almost too obvious to bother to mention. But the reason I mention it is because it doesn't work that way for infinite sets. It's a lot more difficult to increase the size of an infinite set by tossing in elements than it is for a finite set. Just as an example, if we have a countably infinite set, so this is an infinite sequence, all the elements are distinct, they come from a set capital A, and we toss finitely many more elements, say B1 through Bn, from the set B, into set A. So we get the disjoint union. I'm going to assume A and B are disjoint. The disjoint union, it's still countably infinite. It has not increased in size. And that's quite clear because you can just write this infinite sequence. Stick the elements B1 through Bn at the beginning of the sequence, write out the rest of the sequence for the set capital A. You'll have an infinite sequence consisting of each letter from this disjoint union appearing exactly once. As a matter of fact, we can even toss into another countably infinite number of elements. And now we can't put the B's first and then the A's because the B's never end, right? But we can interleave or alternate A naught, B naught, A1, B1, A2, B2. And this is clearly an infinite sequence where each element of the disjoint union of A and B appears exactly once. So the union of a countably infinite set and a countable set, either finite or countably infinite, is again countably infinite. Just to be less formal, if you have a countably infinite set, you can toss in a finite number of elements or even a countably infinite number of elements, and it will not change the size of the set. So that's what I mean by the size being kind of sticky. It's reluctant to become larger. There's a second part to this theorem. The Cartesian product of a countably infinite set and a non-empty countable set is still countably infinite. And I'm going to leave that for you to ponder if you're interested. We can make similar statements for cardinality, for sets of larger cardinality than the countably infinite sets. But, you know, this isn't a class in set theory, although it may seem like it at the moment. So I don't want to get into that discussion. Okay. I'm hoping to kind of wrap up our discussion of cardinality in this video, if I can, so we can move on to other things. Cantor's theorem tells us, as we've seen, that there are infinitely many cardinalities, sizes of infinite sets. And we can get those infinitely many cardinalities by starting with the natural numbers and repeatedly taking power sets. Well, it's then natural to wonder, are there any other sizes of infinities besides the one in this list, the ones in this list? This turns out to be a fascinating tale. Now, you might first think, well, what about the cardinality of the real numbers? Where does that fit? Is that one of these or not? And the answer is that it is. The cardinality of the real numbers is the same as the cardinality of the power set of the natural numbers. So this cardinality, which we've seen is called the power of the continuum, doesn't provide any additional cardinalities beyond what's already listed here. The statement that there are no cardinalities strictly between these first two, so the cardinality of the natural numbers and the cardinality of the real numbers, this is called the continuum hypothesis. Remember that the real line is sometimes called the continuum, and its cardinality is called the power of the continuum. So the continuum hypothesis, which is often abbreviated C, capital H, says that there are no cardinalities, at least between these first two. Cantor himself spent considerable effort trying to resolve this issue of whether or not the continuum hypothesis is true. He tried to prove it or disprove it. A man named Joseph Daubin wrote an article back in 1978 entitled Georg Cantor, the Personal Matrix of His Mathematics. Let me read to you a little bit from that article. Despite Cantor's repeated promises to prove the continuum hypothesis, he was never able to do so. For a time in 1884, he believed he had actually found a proof of the conjecture. But within days, he reversed himself completely and thought that he could definitely show it to be false. Finally, however, he realized that he had made no progress at all, and that the cardinality of the continuum, in other words, the continuum hypothesis, was still an open question. Thus, in the mid-1880s, Cantor was not only faced with mounting criticism from Leopold Kronecker and from others, as I'll discuss later, but he was also plagued with his own failure to determine the power of the continuum. So what he's really saying here is whether the power of the continuum was the next cardinal number after the power of the natural numbers. Such were the circumstances surrounding his hospitalization for what later proved to be recurring cycles of manic depression. Cantor's first serious mental breakdown occurred shortly after his 39th birthday in the spring of 1884. So while this story has a very sad ending, there is one thing that makes me feel a little better anyway, and that is I've been in the same situation where I thought I had a proof of something. Later on, I found out I didn't have a proof and thought maybe the thing was false. So at least I'm in excellent company. But this was just, a very sad story. But the tale gets even more bizarre. Roughly 60 years later, in 1940, the great logician Kurt Gödel showed that the continuum hypothesis cannot be disproved within the confines of traditional mathematics. In other words, the confines of the Zermelo-Fraenkel axioms, possibly tweaked a little bit, which I didn't discuss earlier. But the continuum hypothesis could not be disproved. That doesn't mean it could be proved. It just can't be disproved. It's consistent with the foundations of traditional mathematics. So no contradiction will arise by assuming that it's true. So this is a little vague, and it's going to have to stay that way because we don't really have the time or probably interest in getting more deeply into the foundations of mathematics. It is kind of ironic, I guess. Gödel also had mental problems, and this is unbelievable, but he actually starved himself to death at age 71 because he had an obsessive fear that he might be poisoned to death. It's also a sad story, terrible story. it's a strange predicament for perhaps the greatest logician of all time. You know, even though he was a great mathematical genius, also a very close friend of Albert Einstein. They used to take walks together at Princeton at the Advanced Institute for Advanced Study. They were good friends. I kind of wonder why he couldn't figure out that if he just went out of town, found a grocery store somewhere out of town, he could buy food, it would be safe to eat. But he was so deep into this, whatever it is, that he couldn't reason that much. But in any case, his great contribution, one of many, was that the continuum hypothesis is consistent with the basic notions of traditional mathematics, so it can't be disproved. In 1963, 23 years later, a logician named Paul Cohen, also a great logician, is at Stanford, showed that the continuum hypothesis can't be proved within the confines of mathematics. So the continuum hypothesis cannot be disproved, it cannot be proved. And I'll elaborate on that a little more. But first, if only Cantor had known what Gödel and Cohen had discovered, it might have saved him a great deal of anguish, because he would have realized he wasn't going to be able to prove it, and he wasn't going to be able to disprove it. But it took two great geniuses some decades later to sort that out. So the work of Cohen and Gödel tells us that the continuum hypothesis is undecidable within the confines of traditional mathematics. And by the way, it's not the only mathematical question that's undecidable. Maybe we'll talk some more about that later in the course. Probably not. It's probably taking us too far afield. The axiom of choice, you may have heard of, has the same status. And in fact, it's a more serious issue than the continuum hypothesis. The thing is, there's no universally accepted convention as to the truth of the continuum hypothesis. It's not like the mathematical community has gotten together and more or less uniformly decided that it should be true or it should be false. So every mathematician, or at least every mathematician who actually cares, and that's not really that many, I suspect, must make a decision, a personal choice. They can accept the continuum hypothesis as being true, without proof, because there is no proof. They can reject the continuum hypothesis, in other words, assume it's false. Again, no proof can be had. Or just simply say, I'm not going to decide. See, the thing is, most mathematicians who don't specialize in set theory or logic or something closely related, foundations of mathematics, they can spend their entire career in mathematics without ever needing to make a choice, because it just doesn't come up. Okay? You don't need to make a choice. You don't need to lose any sleep over it. I have not lost any sleep over it. I've been able to do all the mathematics I'm interested in without having to make a decision. Okay. Just on an historical note, Gödel himself believed that the continuum hypothesis should be false. It should be taken to be false. And that the traditional axioms of mathematics are simply not powerful enough to fully characterize set theory and therefore, and also show that the continuum hypothesis is false. There ought to be more cardinalities than the ones in the list I gave you. And Paul Cohen also believed that to be true. So I guess who are we to decide otherwise, Cohen said, a point of view which the author, meaning himself, feels may eventually come to be accepted is that CH is obviously false. I wish I understood what he meant by obviously false, but it's too late to ask him. In other words, both mathematical geniuses felt that the proper way to extend the foundations of mathematics is to include the fact that there are additional cardinalities beyond those in the list I gave you. The statement that there are no cardinalities, let's go back to this list, anywhere between members of this list. In other words, this is a complete list of the cardinalities of infinite sets. That is simply called the generalized continuum hypothesis. And that's in the same boat as the continuum hypothesis. Okay? That's also, you can't prove it, you can't disprove it. So let me conclude this discussion of cardinalities with a few more comments about Cantor himself. I think that's quite interesting. If you're not interested, you can stop the video right now. When most great mathematical ideas, such as Cantor's theories on infinite cardinalities, are discovered, both the discovery and the discoverer are generally met with great praise from colleagues. They may be given awards, asked to visit the universities, to give lectures, and so on. Of course, at the same time, these great discoveries are met with total and complete indifference among non-mathematicians. So, especially since these days they tend to be extremely esoteric. So it's kind of difficult to comprehend, at least for a mathematician to comprehend these days, the extent to which Cantor faced opposition to his new ideas concerning the infinite cardinalities. Not just from some respected mathematicians like Leopold Kronecker, who was a very strong mathematician, but also from philosophers and some theologians. And it's also really kind of hard to comprehend how strong an effect that had on Cantor, on his mental stability. Well, to understand what happened to Cantor, we first have to look farther back in history, I should say further back in history, dating back thousands of years, way back to the Greek philosopher Anaximander. And he and mathematicians of his time, and philosophers as well, wrestled with just the notion of the infinite, never mind how many infinities there are. There was a strong feeling that something that couldn't be conceived of as a whole or completed object didn't exist. So the natural numbers, for example, would not have existed for them. Only those insofar as they could write them down, which is kind of weird because one person could probably write down more of them than another. So in Cantor's day, Christian theologians regarded the idea of infinity in mathematics as a direct challenge to the unique and absolute infinity of God. That alone was a tremendous source of stress for Cantor because he was deeply religious. And he himself was concerned about the relationship between the infinite and God. In fact, Cantor apparently considered his work on what you could call transfinite numbers, that's infinite numbers, infinite cardinalities, to have been communicated to him directly from God. So here's a very religious person who believes he was inspired by God, but at the same time is being stressed out by theologians who are saying he's essentially a blasphemer. Aristotle also had much to say about infinity, and he had a great influence on the general perception of logic and philosophy and things. And he devoted a portion of book 3 of his work called Physics. I've never looked at that. To discussing the notion of infinity. And in chapter 5, this is what he says. I found this quote. Hold on to your hats. It is plain, too, that the infinite cannot be an actual thing, and a substance and principle. For any part of it that is taken will be infinite if it has parts. For to be infinite and the infinite are the same. If it is a substance and not predicated of a subject. Hence, it will be either indivisible or divisible into infinities. But the same thing cannot be many infinities. Yet, just as part of air is air, so a part of the infinite would be infinite, if it is supposed to be a substance and principle. Therefore, the infinite must be without parts and indivisible. But this cannot be true of what is infinite in full completion, for it must be a definite quantity. Well, all I can say is I'm glad I never met Aristotle, because I wouldn't understand a word he said. And there's a good chance he wouldn't understand any of the words I said. And just a little more in chapter 6. Hence, since no sensible magnitude is infinite, it is impossible to exceed every assigned magnitude. For if it were possible, there would be something bigger than the heavens. Our account does not rob the mathematicians of their science by disproving the actual existence of the infinite in the direction of increase, in the sense of the untraversable. In point of fact, they do not need the infinite and do not use it. Well, if you figure out what Aristotle's talking about, send me a little note. Early mathematicians generally avoided the use of the idea of completed or actual infinities. Even Carl Friedrich Gauss, the prince of mathematics, wrote as follows in a letter he wrote to some person he knew, I presume. But concerning your proof, I protest above all against the use of an infinity quantity as a completed one, which in mathematics is never allowed. The infinite is only a façon de parler, that's a manner of speaking, in which one properly speaks of limits. That almost makes sense in a way. It's a lot closer to making sense than, at least it's a lot closer for me, than I can make out of Aristotle's discussion. What's probably most astonishing, Aristotle and Gauss, they were a long time previous to Cantor, and things change a lot over the centuries. But what's more astonishing, I think, is that even some of Cantor's contemporaries, as I mentioned, Leopold Kronecker, he was quite a famous mathematician, took great exception to Cantor's notion of infinity. Kronecker described Cantor in public as a scientific charlatan, a renegade, and get this one, a corrupter of youth. So maybe I should have posted a sign at the beginning of this lecture that this was only for people over 21. I don't know. But in light of Cantor's feelings of divine inspiration concerning his work with the infinite and the negative feedback from Kronecker and from some philosophers and theologians, along with the frustration he felt because he couldn't prove what he believed to be the validity of the continuum hypothesis, and later on couldn't disprove what he believed was false, it's not surprising Cantor came under immense stress. And that's no doubt a contributor to his bouts of depression and so on. Cantor was the first to formulate the continuum hypothesis, which he believed to be true at least up to some point. But he tried for many years to prove it with no success, as I've discussed. Well, and now, of course, we know why. His efforts were in vain because he was never going to be able to prove it or disprove it. Well, it's my personal feeling that the subject of infinite sets, set theory in general, is one of the most fascinating branches of mathematics. I've spent some time studying set theory. It's very difficult once you get past a certain level. I taught one class in set theory at the University of California, Irvine, and I enjoyed it very much, and I think the students did as well. Here we've only just scratched the surface. As you can imagine, the subject of set theory is very vast, and it gets very abstract rather quickly. So we're done with it. I hope you did find it interesting. If not, I hope it didn't do you any harm. It didn't corrupt you in any way. And we're ready to move on to another topic. Thank you for watching this video, and I hope to see you in the next video.